So again, kind of circling back, my name's Jerry Fry. This is track 3, session 3, the Interstate 84 Twin Bridges project in Lackawanna County. We're looking forward to sharing this really exciting project with you. PDH certificates, I mentioned the link to the PDH form earlier, which has been posted by Bob, I believe. Those PDHs will be available shortly after our conference here is over. They might be a little bit sooner, but there's no promise of that. The help desk for this conference, should you have trouble with really anything, is 2021 helpdesk at ashe.pro. That's 2021 helpdesk at ashe.pro. Okay, so we will have 3 speakers today representing our project. Sue Williams, who is a senior project manager for the Pennsylvania Department of Transportation's Engineering District 4 in Dunmore. Has 28 years of experience with transportation design and management, and will be kicking off the presentation. The lead designer of our project is Tim Benner from McTish Kunkel and Associates in Allentown. Tim has 30 years of experience in transportation and bridge design and is currently the vice president with McTish Kunkel and Associates. He has a bachelor's degree in civil engineering from the University of Pittsburgh and is a registered professional engineer in Pennsylvania, Ohio, and Michigan. Also presenting today will be Ben Martz, who is also a professional engineer with McTish Kunkel and Associates. He served as lead structures engineer and assistant project manager on this project. Ben holds a bachelor of science degree in civil engineering from Penn State University and a master of engineering and structures engineering from Lehigh University. He's also a registered professional engineer in Pennsylvania with 12 years of experience. So with that, Sue, I'd like to invite you to start our presentation. And I will jump off the stage here as you do that.
Okay, thank you, Jerry. Good morning. My name is Sue Williams. I was the project manager for the 84 Twin Bridges project, and I appreciate the opportunity to present our project to the conference this morning. I'll be doing a quick introduction to the project, then I'm going to turn it over to Tim Benner and Ben Martz from McTish Kunkel and Associates. They are the project's design engineers. First, a little background about PennDOT in this region. Engineering District 4 is located in the northeast corner of Pennsylvania and includes 6 counties. We're responsible for maintaining 3,932 miles of roads, including 800 lane miles of interstate, the most of any PennDOT district, as well as 2,090 state-owned bridges. The Twin Bridges project is located on the I-84 corridor just outside of Scranton near its connection with I-81, I-380, and historic Route 6. For those who aren't familiar with the area, Scranton is about 120 miles west of New York City, 125 miles north of Philadelphia, and 120 miles northeast of our state capital in Harrisburg. The confluence of interstates and other strategic and priority routes in this area, including I-80, I-81, I-84, I-476, and I-380, provide critical linkage in each direction, and it's vital to the economic health of the area. About 20% of the U.S. population lives within 300 miles of Scranton. The Twin Bridges project is located in Dunmore Borough and Roaring Brook Township, just outside of Scranton in Lackawanna County. You can see that our project is midway between the I-84, I-81 Route 6 interchange to the north and the I-84, I-380 interchange to the south. The Twin Bridges carry I-84 over Roaring Brook and the D&L Railroad just south of Exit 2 with State Route 435, which is also part of our project. The aerial view of the project setting gives you a better sense of the area with the Twin Bridges in the foreground. Exit 2 with State Route 435 to the right and the urban center of Dunmore and Scranton, as well as the I-81 interchange just outside the frame at the top of the photo. A quick timeline on the project. The McTish Kunkel Associate Design Team was selected in April of 2015 and notice to proceed issued in July of that year. The environmental clearance was acquired in February of 2018. Bids were opened in February of 2020 with a low bid of $113 million. The project is currently in its second year of construction with substantial completion scheduled for December of 2025 and project closeout in early 2026. Now I'm going to turn it over to Tim Benner, who will discuss the project's overall development design.
Thanks, Sue. I'm Tim Benner, and I was the project manager for the Twin Bridges project. The current bridges are pictured here looking north towards Scranton. There are 7-span steel twin girder bridges carrying I-84 over D&L Railroad and Roaring Brook. The bridges are each about 1,100 feet long and 40 feet curb to curb, carrying 2 lanes each. Situated in a steep valley, the bridges are about 160 feet above Roaring Brook. That's roughly the equivalent of a 12-story building. The bridges also cross the former E&WV Railroad that can be seen in the foreground. This bridge was built in 1883 and carried the former railroad over Roaring Brook and D&L Railroad, although it hasn't been in service since the 1960s. The photo also shows the curved alignment of I-84 to the right as you go north and the rock cut that's immediately north of exit 2. This rock face is about 130 feet high. The current twin girder bridges are fracture critical and include a detailing typical to the design era that has since been determined to be fatigue prone. In addition to general deterioration over the years, these fatigue prone details have resulted in displacement induced cracking in main and secondary members after decades of fatigue cycles under heavy traffic. PennDOT has undertaken several bridge repair contracts to address the fatigue cracking as well as other general deterioration. In fact, one of the initial items of work on this project was to conduct additional structural repairs to the existing bridges to keep them in serviceable condition as the new bridges were being constructed. This is a view of the project area looking south towards the I-380 split. You can see the terrain is steep and I-84 is bifurcated through the project area with the elevation difference increasing as you get closer to exit 2, where the ramp to State Route 435 southbound goes under I-84 westbound. The median width also varies through the project, widening as you get closer to exit 2. Current traffic volumes on I-84 in this area are around 50,000 vehicles per day. It's also a heavy freight route with 26% trucks. As you can see, exit 2 includes a non-conventional left-hand exit from I-84 eastbound to State Route 435 southbound. I-84 is 3 lanes wide from the I-81 interchange to exit 2, where the left lane becomes exit only. Exit 1, only a half a mile from exit 2, brings in 2 on-ramps in a more conventional manner on the right, one for Tige Street traffic and one for Route 6 traffic. The limited distance between the interchanges makes for a weave area that's challenging to navigate from right to left into the exit-only lane for southbound State Route 435. The current bridge over State Route 435 southbound also has substandard vertical clearance at 14.6 and is highly skewed at 20 degrees. That's 20 degrees in PennDOT terminology, which is 70 degrees for AASHTO. In order to develop a solution, it's important to understand the features within the project area. It may look like an untouched rural landscape at first glance, but this location has a long history. It was the location of the former town of Naog that formed along the railroad between the mid-1800s through the early 1900s. The light gray line you see bisected by I-84 is Drinker Turnpike, which has been in place since the early 1800s. The light gray line to the southwest of I-84 is Brickyard Road, formerly Greenville Road, that connected Naog to Point South. Both are currently little maintained dirt and gravel roads. Roaring Brook is obviously a key feature through the project area, as is the D&L Railroad. These two features bisect the project site, creating access barriers to build and maintain the bridges. Existing utilities include overhead electric and telephone lines, as well as 2 30-inch water mains that deliver water from the Elmhurst Reservoir to Scranton. One of the water mains is located directly underneath the current bridge abutments. We also had remains from the former D&L Railroad complex, including the pump house adjacent to the westbound bridge. The pump house was constructed along with Silver Lake to service the original steam-powered trains. The former E&WV Railroad was also located within the project site and dates to 1884. Although the track has been removed since the 1960s, the bridge, which we highlighted earlier, is still in place over Roaring Brook and the D&L Railroad. The Pennsylvania Coal Company Gravity Railroad was the predecessor to the E&WV steam line and was in service from 1850 to 1884. If you're unfamiliar with Gravity Railroad, they were a system of two separate one-way routes, one for loaded coal cars and one for empty coal cars. Cars were moved on narrow gauge track in a series of inclined planes, each with its own stationary steam engine that would be used to pull the cars up the plane by cable. Downhill movement was powered by gravity. The track through our project area site was a light or unloaded coal car track. The former Scranton Gas and Water Power Plant, in operation from 1910 until it was damaged from Hurricane Diane flooding in 1955, is located just downstream from the bridges. Large portions of the town and the railroad were also damaged during this flood event. The remnants of the former Naog Brickworks factory is located immediately west of the current bridges between I-84 and Brickyard Road. Factory remains are still visible within the I-84 right-of-way. Parts of Old Drinker Turnpike were paved with Naog brick and are still in place. This photo was taken looking south from where the current I-84 bridges stand. The E&WV track runs directly in front of the brick factory, and Brickyard Road can be seen running from the factory to the top left of the photo. Foundations from some of the buildings in the background are still present between I-84 and Brickyard Road. To tie everything together, this is an old map of Naog with the SG&W power plant and D&L pump station highlighted. I-84 currently runs between the two across the former rail yard and the brickworks in the lower right. Both the D&L and E&WV railroads can be seen, as well as Old Drinker Turnpike and the town parcels. We also have several wetland and waterways delineated in the project area. Several could not be avoided and required mitigation. On-site wetland mitigation is constructed as part of, is being constructed below Silver Lake between the two water lines as part of the project. The Music Mountains Barrens Natural Heritage Area is located just northeast of our project by the rock cut. We also had several threatened species, including timber rattlesnakes, identified near but not within the project area. One thing that's not highlighted is several areas adjacent to the project are also part of the Pinchot State Forest or in the process of being transferred to the state forest. As you can see, we had a lot to work around. So now that we know what we're working with, here's what we needed to do. First, replace the twin bridges, which are in poor condition, and do it in short order. We needed to minimize impacts to the traveling public by maintaining 2 lanes of traffic in each direction on I-84 during construction. You'll remember that each bridge can only carry 2 lanes and are twin girder bridges, so staging the existing bridges was not possible. We also needed to maintain traffic on a State Route 435 ramps. Although traffic volumes are not as great as the interstate, the available detour routes are limited, so we needed to minimize any ramp closure durations. Finally, we needed to evaluate the State Route 435 interchange to eliminate the weave condition between exits 1 and 2, provide the required vertical clearance for that movement, and improve safety. Stormwater management and NPDES permitting was also a big concern during design development due to the terrain we're dealing with. All drainage obviously makes its way to Roaring Brook, but there are limited areas available to address the additional stormwater rates and volumes associated with the project, while avoiding or minimizing impacts to cultural and historic resources. And constructability, the key to every project. We needed to develop a design that addressed all the project needs, worked within our constraints, and allowed for construction to proceed with limited restriction. So here's our final product, or at least a rendering. This graphic is a capture from a visualization video we put together for our public involvement efforts. Clearly explaining projects to the general public using conventional 2D plans can be challenging, especially when you're trying to convey complex construction. However, a fly-through video rendered from our project base plans brings the project to life and makes it that much easier for people to understand. One thing you'll notice is that we're eliminating the bifurcation on I-84 and taking the ramp to 435 southbound over I-84 in a flyover configuration with a conventional right-hand exit. To maintain 2 lanes of traffic and fit everything in, we're able to shift the alignment of I-84 eastbound to the median and construct a portion of the eastbound bridge down the middle of the 2 existing bridges while leaving traffic on the existing structures. The height of the existing bridges also enabled us to build the new piers under and around them before touching the existing bridges or impacting traffic. After the portion of the new eastbound structure is completed in the median, we'll shift eastbound traffic to the constructed portion, demolish the current eastbound bridge, and complete construction of the eastbound structure. Both new bridges are being constructed in 3-lane configurations with 12-foot shoulders to accommodate current traffic as well as future redecking. Once the eastbound bridge is built, it's wide enough for both eastbound and westbound traffic to be shifted to the new bridge while the westbound bridge is constructed full width. This approach also allows for construction of the flyover bridge in stages with mainline and only requires a detour to the southbound ramp when I-84 westbound traffic is shifted to the new eastbound side and the current left-hand exit is cut off. This is a view of the new interchange configuration from that same visualization video. Here we're looking south towards the I-84 bridges. You can see the I-380 split at the top of the picture. The weave area between exits 1 and 2 is eliminated with the new right-hand exit and flyover bridge, which is a significant bridge in its own right, having both spans of over 300 feet in length. You'll notice the bifurcation is gone and the new mainline bridges are closer together with a limited median width. Constructability was at the heart of design development for this project. We talked about the terrain on site and the need to work around an active railroad and Roaring Brook, but we also needed to address the lack of access points that were available to get the large amount of labor, materials, and equipment on site for such a considerable undertaking. The construction site is bisected by the railroad and Roaring Brook with a round trip of approximately 10 miles required to get from one side of the site to the other. This is obviously not an efficient way to build some very large bridges. To solve the issue, we looked to one of the resources we had on site, the 1883 E&WV Railroad Bridge. It connected both sides of the project site, but hadn't been in use for over 6 decades. We already needed to address the E&WV property and bridge as part of our environmental clearance process. Lackawanna County purchased the former railroad property and bridge in 1980 to develop it into a trail using in part land and water conservation funds. However, the property had not been developed to date. One of the causes for the delay was the high cost of rehabilitating the old railroad bridge. The use of LWCF money makes it a 6F property. In occupancy for more than 6 months, which we would definitely do, would trigger a conversion and require mitigation. As you may know, mitigation for conversion of a 6F property can be a lengthy process, time we didn't have. We had a need for access, and the county had an old railroad bridge that did exactly that. So the project team, PennDOT and Lackawanna County coordinated with Pennsylvania DCNR at the state level, and DCNR negotiated with the National Park Service at the federal level to agree to a non-conversion determination for the property and allowed us to rehabilitate and use the structure for construction access, occupy the property for the duration of construction, then turn the bridge back over to Lackawanna County for use in developing their trail. The only caveat being the county had to commit to constructing the trail connection by the end of our Twin Bridges project, which they did. That trail is currently under design. In addition to the bridge, we provided a staging area between I-84 eastbound and Brickyard Road to allow access to the southern end of the bridges directly from the interstate and improved Old Drinker Turnpike from State Route 435 to the project site. These connections allow for the free flow of equipment and materials through the project site, provide direct connections to I-84 and State Route 435, and limit impacts to traffic. The access way can be seen in this aerial taken early in construction. On the right, Brickyard Road is being improved to make the connection from I-84 to the old E&WV corridor and bridge site. You can make out the orange temporary protective fencing around the old brick factory between Brickyard Road and I-84 eastbound, which had to be avoided. The access road then follows the old rail corridor under the I-84 bridges, across the E&WV bridge, and over Roaring Brook and the D&L Railroad. You might be able to make out the new decking on the E&WV bridge to the left. Ben will cover the railroad bridge improvements later in the presentation. Multiple levels of access ways were also required to get down to Roaring Brook and the pier locations. We'll show those later in the presentation as well. This aerial is the eastern side of the site with the access from Old Drinker Turnpike in the lower left. You can see Silver Lake in the upper left and the demolition of the former D&L pump station ongoing near the westbound bridge adjacent to the access road. The access from I-84 eastbound is in the upper right-hand corner. The construction access basically makes a figure 8 through the project site connecting I-84 and State Route 4 to 35 and keeps equipment and materials moving in and around the site without impacting the traveling public. Now I'll turn it over to Ben Martz, who will talk about the bridge designs and give an update on construction.
Okay, thanks, Tim. My name is Ben Martz, and I was the lead structural engineer on the Twin Bridges project. As we have seen, the abandoned Erie and Wyoming Valley Railroad Bridge forms a critical link for both construction of the Twin Bridges and for its future use conveying the North Pocono Trail. The existing structure is situated roughly 75 feet above Roaring Brook and 19 foot 6 inches above the active D&L Railroad. It is comprised of 2 simply supported riveted steel I-girder spans, each 96 foot long, and 1 simply supported steel Pratt truss span, 152 foot long. Substructures include stone masonry abutments, 1 stone masonry pier, and 1 steel pier bend, each having a skew of roughly 45 degrees. To ensure viability for its intended future uses, McTish completed a 2-week site assessment in May of 2016, which included detailed structure inspection, survey, and material sampling to support a rehabilitation feasibility study that shaped the final scope of the rehab work. Given the age of the structure and its current use, there were no existing plans or inspection evaluations available. This required complete rigging of the bridge to gain access and gather detailed measurements of structural members along with their current condition. Direct access to the top of the structure was available by walking the top flanges with safety hand lines, as you can see in this photo. Additional access techniques included the use of a man lift for the upper truss portal frame, a pick for the lower levels of the I-girders, and a bosun's chair to inspect the steel pier bed. Various survey techniques were used to establish the existing structure geometry. Conventional survey using a total station retrieved top of steel girder or stringer elevations, along with bearing seat elevations and truss panel points. An unmanned aerial system using a DJI Phantom 4 Pro drone also supplemented the conventional survey in areas with restricted access, particularly the outside face of girders. To efficiently generate the geometry of the steel pier bend, a terrestrial scan using a Faro scanner created a 3D point cloud of the existing bend as captured in this image. Material samples were taken at non-critical areas of the existing steel structure, namely at a truss end block enclosure, a steel I-girder end projection, and at a broken lacing bar on the lower level of the steel pier bend. Steel samples were tested for chemical composition and mechanical properties to support engineering analysis of the rehab design. Chemical testing showed uniform composition throughout the structure that agrees favorably with early low-carbon steels, featuring excellent ductility and weldability. Composition tests also revealed sufficient amounts of chromium, copper, and nickel that supports weathering steel behavior and is indicated by the well-developed rust patina shown in this photo. Tests for mechanical properties indicated minimum yield and tensile strengths of 36 and 58 KSI respectively. The rehabilitation scope of work centers around establishing a safe crossing by removal of the existing timber ties, complete cleaning of the bridge, and construction of a new reinforced concrete deck and barriers. One of the major components of the rehab design was an asymmetric truss displacement needed to achieve a required 22-foot vertical clearance over the active D&L railroad for double stack rail traffic. To avoid impacting the steel pier bend, the I-girders retained their original position, and the required grade differences from raising the truss were taken with variable haunch over the I-girders, roughly 12-inch maximum. Associated with the truss displacement was a modification of the north abutment seat and construction of reinforced concrete retaining walls to support the raised north approach. The vertical raise in the seat elevation at this abutment was approximately 5 feet. Existing tie rod supports at the south abutment were replaced in kind using similarly sized weathering steel members, and stone masonry repointing was also needed in select areas as seen in the photo. Frozen existing metal bearings at the ends of the eye girder unit were replaced with laminated neoprene pads to relieve thermal forces on the steel pier bed. And the mid-level horizontal lacing members of the steel pier bed suffered from heavy corrosion and were also replaced in kind. The bottom of the steel pier bench showed heavy corrosion, especially at isolated connection plates, as you can see here. This condition warranted complete concrete encasement of the bottom of the pier bench for a height of roughly 5 feet. Additionally, a new approach slab with attached barriers was detailed at the south abutment to contain the future trail in this area of very steep terrain adjacent to the abutment. Features such as this, along with barrier protective fence along the entire length of the structure and maximum longitudinal grades of about 4.5%, were incorporated into the design to ensure future pedestrian safety. The proposed typical section over the eye girder spans include an 8-inch reinforced concrete deck with vertical wall barriers and protective fence atop the existing 8-foot deep twin eye girders. Contractor access was provided through the truss span with a minimum of 12-foot horizontal and 18-foot 10 vertical clearance. As you can see, the 12-foot curb-to-curb width was constrained by the existing truss width and was carried over the entire structure. The rehabilitation design meets the Secretary of the Interior's criteria for the rehabilitation of historic structures. Members requiring replacement were done so with in-kind features using weathering steel to closely match the existing appearance. Precise survey of the steel pier bent allowed accurate detailing for the in-kind replacement of the mid-level lacing member as seen here. The north abutment seat modification also incorporates a veneer finish to mimic the existing stonework. Load ratings for the steel truss and eye girders were based on load factor design methodology using PennDOT's Bar 7 software, and the new retaining walls of the north approach were designed with PennDOT's ABLRP software. The existing pier bent was analyzed using a 3-dimensional finite element model in STAD with manual LFD specification checks. Geometry for the steel pier model was generated from the 3D survey point cloud that we saw earlier. A wireframe figure was created from the point cloud to establish nodal geometry coordinates, which could then be imported directly into STAD to create the 3D analysis model. Having established appropriate construction access, our focus turns now to the replacement of the I-84 twin bridges. The design was developed in accordance with the AASHTO LRFD bridge design specs as supplemented by PennDOT's Design Manual Part 4. Layouts of the replacement structures were driven by the intended traffic control approach and site constraints, including the future North Pocono Trail, Roaring Brook, Delaware-Lackawanna Railroad, active PAWC water lines, and existing substructures. Both bridges are generally on tangent horizontal alignments, except for the northern end spans that are influenced by the curved approach roadway, which produce transitions to full super elevation on structure. The vertical profile over each bridge is also predominantly tangent, except for sag curves that spill onto each end span. The resulting span arrangement lent to the use of 4-span continuous composite steel plate girder superstructures with spans ranging from 228 feet to 330 feet max. To achieve proper span ratios, the north abutments had to be placed directly over one of the active PAWC water lines, requiring relocation of the water line to avoid the proposed foundations that we'll talk about later. The overall width for each superstructure was 63 foot 4.5 inches, which was dictated by the need for 3 12-foot travel lanes, 12-foot shoulders due to heavy truck volumes, and MASH compliant F-shaped barriers. The final girder framing arrangement included 5 girders at a 13-foot 9-inch spacing with 4-foot 2¼ inch overhangs, and the selected girder web depth was 10 feet. With significant clearance under the existing bridges, early action pier construction was vital to minimize impacts to traffic. Half-width staging of the eastbound bridge was selected due to constructability concerns with restricted median width and to avoid closely spaced bifurcated superstructures. The eastbound roadway profile was designed in coordination with the 10-foot girder web depth to ensure there was satisfactory clearance to build the new pier caps underneath the existing steel girders. The eastbound roadway horizontal realignment was also set to position the half-width superstructure to avoid interference with the existing bridge. Staging of the eastbound bridge also satisfied the need for full-width construction of the westbound bridge and roadway needed to accommodate a required 9-foot vertical profile adjustment for the new flyover bridge. The staging sequence begins with constructing half-width of the new eastbound bridge in the median under existing traffic patterns. Of course, all the eastbound piers and the staged abutments have been built prior. 3 of the 5 girder lines are erected in the stage, along with 32 foot of deck to support 2 lanes of staged traffic. Next, both lanes of I-84 eastbound traffic are shifted to the new half-width structure while the entire existing eastbound bridge is demolished and the remaining portion of the new eastbound superstructure built. Take notice that this stage requires erection of the remaining 2 girders, which introduces temporary stability concerns that we will discuss in a moment. 2 separate deck pours, including a closure pour between girders 2 and 3, was specified to deal with large dead load deflections. Following completion of the eastbound bridge, 2 lanes of westbound traffic are then crossed over so that all 4 lanes of I-84 traffic are on the new eastbound bridge. Under this stage, the existing westbound structure can be demolished completely and the new structure built full width. Generally speaking, design of the twin bridges was carried out using PennDOT approved software to perform LRFD specification checks. Those aspects of the design requiring refined methods of structural analysis were done so using a parametric 3D finite element model in CSI Bridge. With respect to the superstructure, PennDOT STLRFD software was used to design the steel plate girders, while the CSI Bridge model provided verification of live load distribution, cross-frame forces, thermal loads for bearing design, lateral bracing forces, and construction staging analyses. The steel plate girders use grade 50 weathering steel with HPS 70W steel and flanges over the piers. 13 field splices limit field sections to a maximum of 105 feet to accommodate shipping and girder erection. Plate sizes were detailed as uniform as possible with 2 discrete flange widths, 34 inches over the piers and 28 inches elsewhere. The 10-foot web depth was also matched on the flyover bridge to realize fabrication economies of scale. Intermediate steel cross frames used a K-frame configuration, and top flange lateral bracing was used along the entire length of the bridges in both fascia bays to aid in construction staging. Design build high-load multi-rotational disc bearings were specified since the maximum design vertical load capacity of 2,000 kips fell outside normal PennDOT standards. Substructures were detailed on the contract plans based on preliminary bearing heights and bearing seats adjusted in construction after the final bearing designs were complete. Being complex structures, construction staging analyses were carried out in CSI Bridge to ensure a feasible conceptual girder erection sequence was presented on the construction plans. Additional staging analyses specifically addressed global stability during the staged eastbound deck pours, particularly for the 2 girder condition that we saw earlier. This particular stage required temporary lean-on bracing be installed at intermediate points between the stages to stabilize the 2 girder system during the deck pour. The critical stage deck pour was simulated in CSI Bridge for an unbraced condition since non-composite dead load deflections were on the order of 6 inches. The resulting instability led to inclusion of the temporary lean-on bracing, and the updated model shown in the graphic to the right was used to design the temporary bracing and establish the required brace points that were shown on the construction drawings. Both eastbound and westbound structures were designed with reinforced concrete cantilever abutments and hammerhead piers. The abutment design was carried out using PennDOT ABLRFD software, and due to the length of the wing walls, mechanically stabilized earth U-wings were used at each corner of both bridges. Pier heights range from 68 feet to 150 foot max, with the majority of the piers in excess of 100 feet. To accommodate jacking of the steel superstructure for future bearing replacement, the pier cap width was set at 6 feet and the pier stem tapered to the top of the footing. This geometry resulted in slender piers conducive to consecutive fixity, and in fact, all piers were fixed on both bridges. The CSI bridge model was used to establish longitudinal force distribution that was incorporated into Viathor bmartz software, responsible for LRFD specification checks of each pier. In addition, nonlinear P-delta analyses in CSI bridge further evaluated slenderness effects, particularly for the eastbound piers subjected to the in-service half-width stage superstructure. The proportions of the piers mandated the use of measures to control heat of hydration associated with mass concrete, since footings average 10 foot thick, and with plan dimensions on the order of 30 to 40 foot square. A thermal control plan was developed by the contractor, incorporating circulated water through PVC pipes to limit concrete temperatures for proper curing. Also, architectural treatment was specified for all piers in an effort to preserve the historic architectural features of the site, especially considering the new piers will be on full display for the future North Pocono Trail. The theme of stone masonry from the ENWV Railroad Bridge and the brick produced at the former NAOG Brickworks drove the selection of an architectural treatment pattern. Ashlar stone heavy cut was chosen as a blended pattern to incorporate the stone masonry and brick theme. These photos show the evolution of the design from conception with the ENWV Railroad Bridge masonry pier to the plan specification and then to the physically constructed pattern. An array of foundation types were required due to variable subsurface conditions across the structures. The south abutments used driven HP 12x84 piles approximately 40 foot long. Dynamic pile load monitoring was specified for all test piles. The piers were generally founded on sandstone bedrock, except for eastbound Pier 3, which used 48-inch diameter drilled caissons. Due to the thicknesses of the pier footings and the steep rock profiles, substantial rock excavation was required, particularly at eastbound Pier 2, shown in this photo. The eastbound Pier 3 caissons were roughly 60 feet in length, including 13-foot rock sockets. Cross-volcanic logging and thermal integrity profiling were required at each caisson. The north abutments were founded on 9 and 5/8-inch diameter micropiles, approximately 90 feet long. Micropiles were used here due to the presence of larger boulders in the north approach fill, as well as that portion of the PAWC water line to be left in place after its relocation. Both proof and verification load tests were required during micropile installation. Construction began on the Twin Bridge project in April of 2020 and has persisted through the COVID-19 pandemic. McTish was granted approval to perform aerial drone flights to monitor construction status, and some of the aerial photos will be seen on the following slides. A large portion of the first year of construction consisted of establishing site access, temporary stream crossings, and grading stormwater and wetland mitigation basins. As can be seen in the upper portion of this photo, median widening of I-84 eastbound, or the rightmost lanes, was completed first in order to establish a construction access lane for the southwest staging area. Structure work has focused primarily on the eastbound substructures. The contractor chose to defer complete rehabilitation of the ENWV Railroad Bridge until later in the project and selected to instead install timber decking for temporary construction use. Excavations for the Flyover Bridge Pier are ongoing, and the contractor is currently constructing a temporary soil nail wall to support the pier foundation installation. It's expected to occur this summer. Additionally, a roadway median excavation has been completed in preparation for construction of the realigned eastbound roadway that will tie into the staged mainline bridge. SR 435 ramp traffic is currently being maintained during these operations. Construction of the first stage of the eastbound bridge south abutment is ongoing, and the eastbound Pier 1 is nearing completion. Installation of the drilled caissons at eastbound Pier 3 is also progressing, with about a third of the caissons installed to date. The PAWC waterline relocation is expected to occur later this summer after the pier footing is completed and backfilled. Building the pier caps in close proximity to the existing steel posed some constructability challenges, especially for the top cap pour within roughly 2.5 feet of the existing steel at eastbound Pier 1. This will be the minimum clearance with offsets approaching 4 feet for piers 2 and 3 on this bridge. The contractor used a creative slipline technique to make this top cap pour with no major issues. After overcoming the significant rock excavation, eastbound Pier 2 is beginning to take shape. The base plinth was completed last fall, measuring roughly 12.5 feet wide, 30 feet long, and 25 feet tall. With the second stem pour almost complete, the cap construction should be starting soon. An installation of the drilled caissons at eastbound Pier 3 is expected to extend into early June. These photos capture one of the first concrete pours, as well as a recently completed caisson ready for CSL and tip testing. And now we'd like to show a little video of flight through the active construction site to get a first-hand look at construction progress. Beginning on the southern approach to the bridges, you can see the southwest staging area and construction access off of I-84 eastbound. Brickyard Road is in the background, forming the linked access roads leading under the bridges. The eastbound south abutment construction is progressing with footing being reinforced and formed, and the Pier 1 cap pour is taking place. The NW Railroad Bridge is in service with its temporary timber deck, and the first of 2 temporary stream crossings is in place around the base of the steel pier bed. Adjacent to the railroad bridge is the northeast staging area, with the wetland mitigation site on our right and a stormwater basin located on the opposite side of the northeast access road leading up to Old Drinker Turnpike and Silver Lake. As we move under the bridges, you can see the various access roads leading to Pier 1 and to the temporary crossing of Rolling Brook. This is the second temporary stream crossing in place directly underneath the bridges. Eastbound Pier 2 stem forming is taking place here, and at this point, it has reached a height of roughly 80 feet. You can also notice in the background the setup of the concrete pump truck for the Pier 1 cap pour. This is the final cap pour, and pump truck's pumping roughly 110 feet to the top of the cap. As we move up from under the existing bridges, you'll get a quick look at the eastbound Pier 3 caisson progress with drilling taking place. And behind the Pier 3 excavations, you can see access cut in for the PAWC water line. And another view of the median excavation ready for the first stage of eastbound roadway realignment. This is also a good view of the steep hill slopes on the western side of I-84, as well as the rock cut in the upper portion of the screen. Approaching the site of the new flyover bridge, you can see the ongoing excavation and installation of a temporary soil nail wall. The new pier will be located roughly where the construction equipment is now. The flyover bridge pier will also be founded on drilled caissons, which are expected to be installed this summer after the eastbound Pier 3 caissons are finished. Traffic is currently being maintained uninterrupted. As you can see, the temporary barrier set up to protect not only the I-84 main line, but also the SR 435 ramp traffic around this construction zone. At this point, we'd like to take a moment to acknowledge our project team that included AECOM, Aegis, L&V Engineering, and Aero Land Solutions. We'd also like to acknowledge PennDOT with Sue Williams as the project manager, FHWA, and JD Ekman, who is the contractor for the project. This concludes our presentation, and we'll welcome any questions at this time.
Ben, thank you very much. I appreciate that. I would just like to start off by thanking Sue Williams of PennDOT District 4, Tim Benner, and Ben Martz of McTish, Kunkel and Associates for an excellent presentation today. It looks like you guys ran into just about every snag you could on the project, and I wish you luck during construction. Before we go any further with questions and answers, there's just a brief housekeeping announcement. I just want to let people know that after today's session, you'll be automatically redirected back to the main lobby and then you will have to re-choose the track for your next session. Track 1 for planning and design, track 2 for innovation, and track 3 for construction. Also, I want to let you know that a recording of this session will be available for later review on the Ash National YouTube page. And also, please remember to submit your PDH forms after today's session. I posted those links in the general chat. I'll also do so in the Q&A so that you can get to that. With that, let's go ahead and get to some questions. Our first question today is from Reese Keller, who asks, were any bridge acceleration techniques used to reduce construction duration, or was that not a concern on this project due to location and the ability to maintain existing capacity?
I guess I can take that one. Yeah, generally based on the location and our ability to maintain traffic, ABC techniques really didn't come into play on this particular project. We were able to construct it conventionally without too much impact to the traveling public.
Very good. We have a question here from Gerald Fry, who some of us know. Jerry asks, was any consideration given to maintaining the left exit to reduce costs for the flyover?
Jerry, that's the VAC question. So yes, that was analyzed early in the project when we were looking at the interchange configuration, how traffic moved through there, and what we would have to do to fix that and build this particular project. If you remember, there was a vertical clearance issue at the current left-hand exit bridge. It was only 14.6, and it was highly skewed. So if we would have kept that in place, we would have, with the widened structures, geometrically it didn't work real great, and we would have had to raise profile on 84 westbound going into Scranton considerably. So what happens with that is if you keep that bifurcation going, or if you remember, we moved the eastbound structure into the median where it's going to be right adjacent to the westbound structure. If you kept that bifurcation, the eastbound structure would have been about equivalent to the bottom flanges of the westbound structure. So even from a maintenance standpoint, when you're snow plowing through there, you'd be blowing snow right onto the girders on the westbound structures because of that bifurcation. That was a big concern too. The reconfiguration with the flyover, obviously a little bit more expensive, but it did address a safety issue long term. And in the grand scheme of the project at $110 million, it really wasn't, the cost differential really wasn't that great.
Thank you, Tim. One last question here. Can you comment on the need for a 6 construction season duration for this project?
Yeah, I can start that, and Ben, I can kick it over to you. It is a large undertaking, and in order to get it all done without impacting traffic, takes a long time. We also have a couple of restrictions in there for those stream crossings, but generally it takes a long time to build these 2 structures, actually 3 structures. That flyover structure is over 620 feet long. That's a big structure too. It just takes a long time to work this stuff around traffic. That generally drives it. Ben, I don't know if you wanted to follow up on that.
Yeah, the only thing I wanted to add was, you know, just to speak a little bit about where we're at right now in construction and where we're headed. Where the contractors actually proposed a more aggressive schedule. So within that, you know, contract pre-bid schedule, we are trying to push ahead to minimize that duration, but the COVID pandemic threw a little wrench in things with material acquisition being an issue and kind of slowing things down a little bit. So we're currently right now we're on track based on our pre-bid schedule, behind on the contractors more aggressive. But at the end of the day, we're still looking at that 5 or 6 year time frame for completion, permit closeout.
A question that I had as I was watching the presentation and looking at those haul roads, and I'm sure you've addressed it, but how are they going to get beams delivered and get them to the site?
Yeah, I can speak on that a little bit. So we developed a conceptual girder erection sequence, and under the assumption that the girder segments were going to be delivered via mainline on the existing bridges or portions of the new bridges. So, of course, the existing bridges were rated, and like I mentioned in the presentation, the girder segment lengths were sort of minimized there to around 100 feet, so that we limited our weights for use on those picking from the existing bridges. And I believe, speaking with the contractor, they're holding with that same concept. They're going to bring the girders in, do short term. We have short term single lane closures, night work, so on and so forth, to achieve that. But the girders, that concept should hold. They bring them in on the main line.